Okay, good morning, class. This tutorial basically is about AC power, and let me try to link to the previous tutorials and how do we approach the problem. In previous tutorial, we have learned how to analyze and AC circuits. Okay, AC circuits is basically consists of uh, sources, basically consists of sources, right, with a certain frequencies. As I mentioned, in order to use phasor analysis, all the sources, if more than one, must have the same frequency, right? If not, you need to use the principle of superpositions. Okay, for a linear circuit, suppose that you have a AC source, your signals will have the same frequency, but however, there will be a phase difference between each of the signals, and the amplitude will also be different. For AC signals, basically we have the peak values, frequency, and a phase angle. Okay, this peak values will basically be used in the calculations of your average power. Now, suppose that you put these two signals together in time domain, the phase angle between them is called the phase difference, and this phase difference will also be used in the calculations of your average power. And basically, we know that power is defined as voltage times current. In AC signals, we have voltage and currents as functions of time, and it is characterized by the peak values, right, the frequency, as well as the phase angle. If you multiply these two signals together, this is called the instantaneous power, in the sense that you can calculate the power at any particular time instance. Okay, in power engineering, what we are interested in is the average power. Since AC signal is periodic signals, which means that it is repeated within a period, okay, which is determined by the frequencies. Okay, in calculating the power, usually we'll take the average over a period t. Okay, which means that you should integrate the instantaneous power over a period from 0 to t to calculate the so-called average power. And it is divided by t. We know that integration is the area under the curve. So this basically gives you the total within one period, and you divide by this period will give you the average power. Now it can be shown that if you put these signals into here and then put this into the integrations and try to integrate it over time and substitute capital T, the periods, and t equal to 0 into it, eventually it will reduce to this equation. Okay, the proof is in the notes. You should read through it, convince yourself that this is true. Okay, after that, remember it, right? In circuit analysis, most of the time is that you need to read the derivations of some of the formulas, right? Knowing that this has been shown, and then after that, we will use it. Here, it says that the average power, right, which is the power over a period, okay, or is basically equal to half Vmim cosine theta v minus theta I. Right? Take note that theta v minus theta I is actually referring to the phase difference between the voltage and current. Now, to summarize, average power can be calculated by knowing the peak values of the voltage signals, the peak values of your currents, divide by 2, and then multiply by cosine of the phase difference, right, between the voltage and current. Now, as I said, why this formula, why half, right? Read through the notes, you understand that this was derived, okay, based on substituting these two signals into the instantaneous power and integrate it over one period, divide by periods to give you the average power. So you need to remember this, right? Remember this. Basically, this is how we calculate the average power, which is called the effective power also, for AC circuits. And these are the important parameters, okay, which means that in order for us to know the real power or the average power, okay, we basically need to know the peak values of our voltage, peak values of our currents, and we also need to know the phase difference, okay, between them, so as to use this half VMIM, the peak values, multiplied by cosine of the phase angle. Now, the cosine of the phase angle plays an important role in power engineering. It is called the power factor, right? It's just a name given to this cosine theta. Theta is the phase difference, okay, because this power factors will be used in certain corrections, right? We call power factor corrections to design capacitors, right, so as to achieve some optimal performance. This we will discuss in the next tutorial. So for this tutorial, take note that in order for us to know the effective power or average power, we basically need to know the peak values of the voltage and current and the phase difference between them. Okay, and AC signals basically is easier to analyze in phasor form. The phasor forms of these two AC signals, as we know in the last tutorials, right, can be represented by a complex number, okay, where the magnitude of the complex number in polar forms is basically your maximum values, right? And for current, okay, that means that suppose that you have a voltage source connected to a load, and it resulted in a current flow, right? Resulted in a current flow. Okay, this current will have the same frequency, and it will basically have a certain phase difference, right, with respect to your voltage. Okay, if you plot it in phasor forms, basically this is the phase angle with respect to a reference. Our reference is actually this cosine omega t. Remember, phasor is a rotating vector. This vector will be rotating, thus generating AC signals. But for analysis, we freeze it at a certain time instance, right? In particular, we make our reference cosine omega t, and the rest will be with respect to the reference. Basically, in this case, we know that the phase difference, right, between the two signals, voltage and current, right, is actually used in the calculations of the average power. And to get the other parameters from phasors, basically you need to take the modulus of your signals. Right? Remember, P is equal to VMIM cosine theta divided by 2. And VMIM is actually the modulus of your phasors. That means that if you have a complex phasor forms of the voltage, you need to take the modulus, right, of it. In polar form, you just take directly these values. These are the modulus. In rectangular form, you have to take the square of the real part, square of the imaginary part, and then take square root. Okay, as for the phase difference, right, as I said, it's just the difference between theta v and theta I, the angles, okay, which the vectors make with respect to the reference. So we take the difference and we can get the phase difference. Now, average power, as I said, is the magnitudes of the peak values of the voltage and currents multiplied by the cosine of the phase difference, right, between the signals. Okay, which means that to find the power, basically you can relate it to last week's tutorial by saying that I need to find two things, right? I need to find the voltage across a certain load, okay, which means that if you have a certain load, you're interested in the power of the load, then you need to find two things, right? What is the voltage across this load? What is the current flowing through this load? Okay, after that, you get these two signals. Then you extract the parameters, the modulus of your voltage and current based on the phases representations. And you also take the phase difference between them, right? Between this voltage and current by subtracting these two. And after that, we can use it to calculate the average power. Okay, let me show you the phase difference between various types of loads. Okay, if I have a voltage across the loads and a current is flowing through it as a result of the potential difference, depending on the types of loads, you have different phase difference between the voltage and current. Okay, we know that there are basically three types of basic components that we have learned in this course. Okay, first is a pure resistor. Now, if you have a pure resistors, this Z, right, is basically equal to R. And we know that if we divide, right, if we divide the complex number in polar forms, okay, it's easier to us to perform the computations, operations, because you just divide the modulus and you subtract the phase angle. Okay, if you go back to here, R in polar form is actually R0, right? You need to be able to transform from rectangular form to polar form. Okay, rectangular form over here means that there's no imaginary part, right? No imaginary part. Polar forms basically means that this aligns with your reference axis, it's real. Now, if we do these divisions, okay, then we can see that V theta V divided by R0 resistors means that the modulus is just V over R, while the angle is just theta V minus 0, right? Theta V minus 0 is theta V. Okay, this means that the phase angle of your current is actually the same as the phase angle of your voltage. This is easy to understand because basically resistor is a scalar value. And if you divide this complex number by a scalar value, you just scale the magnitude, right? You just change the magnitude. In phasor form, basically this means that your two vectors are rotating together without any phase difference, right? Without any phase difference. Now, in terms of a power, it means that your power factor is equal to 1. Why? Because power factor is cosine of the phase angle between voltage and current. If theta is equal to 0, no phase difference, cosine 0 is equal to 1, right? So for a resistive load, pure resistive load, your power factor is equal to 1, and the average power is therefore just half VMIM, right? Half VMIM because cosine theta is equal to 1. Now, take note that for resistors, because Ohm's law applied, V is equal to IR, right? V is equal to IR. Okay, therefore, you can also substitute this Ohm's law, all right, into here. In fact, here I is equal to V over R. Then you can calculate the average power based on V squared over R. Okay, if you substitute V into here, you can also calculate it based on I squared R. Okay, the only difference is that here, right, we have half, right, and that was derived based on this average power, half VMIM cosine theta, cosine theta equal to 1. Therefore, we can calculate the average power by simply knowing the peak values. Right, this is because there's no phase difference between them. So remember, for resistors, you can actually calculate your average powers in various forms, right? VMIM half, or half V squared over R, or even half I squared R. Okay, but in time domain, this basically means that your voltage and current are in phase. If I plot another one, this is how it looks like. Okay, both will reach the peak values at the same time. Okay, both will reach 0 at the same time. There's no phase shift between them. It means that the magnitudes only different in magnitudes, no difference in phase angle, right? Because resistor is a real number, scalar. Okay, but we have other types of components, namely we have inductors and capacitor as well. Now for inductor, we know that it can be represented, right, in this form, j omega L in AC circuits, and omega is the frequency, j is the imaginary number. In polar form is equal to omega L 90 degree, right, because j is on the y-axis, so it's making an angle of 90 degree with respect to your reference. Therefore, we have a magnitude omega L, angle 90 degree. Now, we know that, right, if we divide two complex numbers in polar forms, we just divide the magnitude and take the phase angle between them. Suppose that we go back to this load, Z is an inductor. Right? That means that assume that this load is a pure inductor. For pure inductors, your impedance is omega L 90 degree in polar form. Okay, if I divide this voltage by this impedance for the inductor, then they are in polar forms, which means that I just divide the magnitude, this by this, and I subtract the angle, theta V minus 90 degree. Okay, this means that your current, right, is lagging behind your voltage by 90 degree. Now in phasor form, this is how it looks. You have a rotating vectors V, and your current flowing through an inductor is always lagging behind your voltage by 90 degree. Right? Okay, this means that if I apply AC signal over inductor, there will be a current, and this current will always be out of phase with respect to my voltage by 90 degree, and it is lagging behind. Okay, now we know that power factor is cosine theta. If theta is 90 degree, then basically cosine 90 is equal to 0. Okay, which means that there's no real power if you have a energy storage element, pure energy storage element, right? Okay, in fact, these are called energy storage element, right? It stores energy, it does not consume energy. Energy is consumed by resistors, right, which dissipate heat. And for energy storage elements, there's no real power, right? It does not consume any real power. Okay, next, if you plot it in time domain, this is how it looks like. Suppose that I have a voltage and a current. Okay, then they will be out of phase by 90 degree. 90 degree means a quarter of a period, right? Because one period is 360 degree. So one quarter of periods is 90 degree. The voltage and currents are not in phase, but there's a phase difference between them, and this phase difference is 90 degree. We not only that, current, right, is lagging behind. Okay, you can see that if we go by time domains, this voltage will reach the peak first, then followed by the current, right? So the voltage is in front, the current is behind. So I lag V by 90 degree. Okay, next, let us look at the capacitors, right? For capacitors, as I mentioned to you, right, remember in this way, negative J omega C directly, right, is from here, because 1 over J is negative J. In polar form is magnitude 1 over omega C, angle negative 90 degree, because my now is negative J, right? Negative J is here, so it's making an angle of negative 90 degree with respect to your reference. So suppose that you find the currents V over Z, right? V over Z divisions It means that here consider a pure capacitor. Pure capacitor. V over Z. Z is equal to 1 over omega C, negative 90. Right? Since this negative 90 is at the denominator, so we have theta V minus negative 90. Then it becomes positive 90, right? Positive 90. So this means that the current is leading now, right? Is leading your voltage. Current is leading your voltage by 90 degrees because it's theta V, the phase angle of your voltage, plus 90, right? Plus another 90. Okay, which means that the angle between voltage and current is still 90 degrees, right? Therefore, cosine 90 is equal to 0. So similarly, your capacitor does not consume any power, any real power, right? The average power will be equal to 0 because it's stored energy. Now, in terms of time domain signals, this is how it looks like. Right, just now it was the other way around. Your voltage in front of your current. Right now is current in front of your voltage. Okay, that means that current is leading your voltage by 90 degrees. Any questions so far? Okay, so to summarize, three types of loads: resistors, right, real values; inductors, positive imaginary values, okay, the impedance; capacitors, negative imaginary values. So therefore, it leads to different phase angle between voltage and currents, right? When you have pure resistor, pure inductor, pure capacitor as load, right? There will be a certain phase difference between them. So in the case of resistors, right, phase difference 0. In the case of inductors and capacitors, phase difference are 90 degrees, but there's a difference, right, in terms of whether current lead voltage or voltage lead current. Okay, but for most loads, right, it would not be just pure resistor, pure capacitors, and pure inductors. In fact, you have combinations of the loads. Okay, but however, after you simplify them, right, they can be simplified into some equivalent impedance. Okay, if after you simplify them and you get an equivalent impedance Z, which consists of a real part and an imaginary part. Okay, now if your imaginary part is positive, right? If your imaginary part is positive, we call it inductive. It not necessarily means that there's only inductor, right? It just means that overall your reactance is positive. Okay, why we call it inductive is because we know that inductor has a positive, right, reactance, while capacitor have a negative reactance. Okay, we call it inductive because it's not really inductors, it's just dominant, right, by the inductive property. For example, right, I just show you a very simple example. Suppose that I have a inductors J5. Okay, if I connect to a capacitor negative J2, okay, overall is positive, right? Overall is positive. So my inductor dominated, right, over the others components, the capacitors in this case. Okay, therefore, I get a positive values over here, okay, which means that it's inductive, right? Now, suppose that after you combine the loads, the equivalent values give you a negative imaginary numbers. We call it capacitive. Okay, as I said, because capacitor, right, has negative reactance, negative J omega C, and if I see a negative values in my imaginary parts of my equivalent impedance, I call it a capacitive, right? Means capacitor dominance. For example, if I have negative J5 for capacitance, right, and I connect in series with an inductors of negative J2, now in this case, the overall will be negative J3, right? Overall will be negative J3, which means that the capacitive effects, right, dominant. So remember, inductive capacity doesn't mean only inductor, only capacitor. It just means that the equivalent loads has positive, right, or negative reactance. Now here, I want to say that in this case, right, if you put it into polar forms, the magnitude will be the same because square real part, square imaginary part, even is negative, square become positive. So the modulus is the same. The difference is the angle. Right, one is positive, one is negative. Why? Because here it is negative. So you end up with a negative angle. This is positive, you have a positive angle. Okay, if you go back to this again, suppose that your load is inductive and this is your impedance. Okay, and this is a positive angle, right? Therefore, your current will still be lagging behind your voltage. It's just that the angle is not 90 degree, right? For pure inductor, the angle is 90 degree. For inductive load, your current will be lagging your voltage by an angle, right? Which is not 90 degree, but it is still lagging behind your voltage. So this is called inductive load. For capacitive load, right, because it's divided by this, okay, this means that current is equal to V divided by Z. This is negative. Theta V minus negative of this angle make it leading, right? Make the current leading your voltage by a certain angle. This angle is depending on this, right? This is basically your theta. This negative theta, this theta. Any questions? Okay, so this is just a brief review of the lectures before we start the tutorial. Okay, let us look at the tutorial problems now. Take note that there's this remark here for question 1 and 2. All the given values are in maximum. That means this represents the peak values, right? Else are in RMS value. Okay, let's look at question 1. Find the average power absorbed by the 10 ohm resistor. And we are looking at the AC power, right? Okay, so how do we link up with the previous tutorial? In the previous tutorial, right, the questions will face this way. Find the voltage V0 across the 10 ohm resistor, right? For example, find the voltage V0 across the 10 ohm resistor. Okay, here the question says that find the average power, okay, but it's actually related to finding the voltage, and then we use the voltage to find the average power, right? Because why? We know that the power across these resistors in AC analysis is half V squared over R, correct? Half V squared over R, which means that we need to find the voltage across it, square it, divide by R, which is 10, divide by 2. So basically, the first part is still your circuit analysis, find V0, right? Then you use V0 to find the power. Okay, of course, we know that for resistors, right? This is purely for resistor because for resistor, I is equal to V over R. Okay, therefore, your average power become half VI because cosine theta is equal to 1, right? There's no phase difference between voltage and current. This means that you can either use half V squared over R or you can also use half I squared R. Okay, that means that to find average power, you have 3 choices. First, you find V0, then use this one. If you want to find this current I, then you use I square RL. Okay, if you want to find both voltage and current, then you use half VI, right? Half VI. So this, all three are fine for resistor, right? Take note that this is only for resistor because of the fact that the voltage and currents are related by resistor only for a resistor. Okay, in this question, I will use this one, right? Which means that I will find V0 first. How do I find V0? Use any method, right? Use any method. Okay, here let's analyze this circuit. Okay, this circuit actually is divided into two parts. Like this is the ground. Okay, but the circuits are related in the sense that this current flowing through the left-hand side will affect this circuits on the right-hand side in terms of this dependent source, 8I0, right? 8I0. And the voltage across the 10 ohm resistors will affect, right, the voltage across this terminal over here. Okay, which means that they are coupled, right? I0 appears here, V0 appears here. That means both, right, appear in left-hand side and right-hand side. So basically, if you look at the left-hand side first, there's only one loop, right? So it's easier to use Kirchhoff voltage law to go around this loop, write down one equation, right? Firstly, voltage across this source is known, 820. This is the voltage, right, across this source. Okay, over here, we know that this is the voltage across the 4 ohm resistors, Ohm's law, 4I0. Ohm's law. Current is I0, right? Next, the voltage across this is given as 0.1 V0. So I'm using Kirchhoff voltage law. This voltage is equal to voltage across the resistors plus the voltage across the dependent source. Here I get one equation. Okay, but I have two unknowns, I0, V0. Right? So in circuit analysis, basically you look at the number of unknowns and then you know how many equations you need, right? Then you proceed to solve it. So you know that you can't solve it here because there are two unknowns, right? In fact, we only deal with half of the circuits. We have not analyzed the other half of the circuits on the right-hand side. So this means that you should proceed to the right-hand side to look at these circuits. Now in these circuits, we have two meshes and only one node, right? Only one node. So perhaps it's easier to use KCL, right? Or something similar to nodal analysis. I define a node voltage V1, and then I look at the current flow in and out of the nodes. Okay, this one I'll follow the convention outflow, 8I0 outflow, right? And then this one I'll use outflow as well because normally, right, the current will flow to the ground. Therefore, I have V1 divided by J5 outflow. Okay, this one also flow to the ground, right? So I have V1 divided by the total impedance, right? What is the total impedance? Series 10 plus negative J5, right? 10 plus negative J5. So V1 divided by the total impedance, all outflow, no inflow, inflow equal to 0. So I get another equation. Now, if I go back to equation 1, I realize that, right, I0 is okay, but I want V0, not V1, right? I want V0, not V1. So I should try to relate V1 to V0. V1 is here, V0 is here, and you can see that actually you can use voltage division law to find V0 based on V1, because basically if this is V1, right, it just means that the voltage across here is V1. Okay, voltage across here is V1, and here you can see that V0 is a portion of V1 according to the ratio of the impedance. Z1 divided by Z1 plus Z2 multiplied by V1. Okay, as I said many times, even if you cannot remember voltage division law, or you cannot visualize voltage division law, then use Ohm's law. Ohm's law says that you find the current flowing through the resistor, which is I1, right? Then you multiply by 10. So I1 10 is your V0. What is I1? I1 is V1 divided by the total impedance. I1 is V1, right? Divided by the total impedance. So I1 times 10 give you V0, which means that I get the relationship between V0 and V1. So I express V1 in terms of V0, then I substitute into here, right? So that everything will be in terms of V0. So the next step is to substitute equation 3 into equation 2, right? So as to get an equations with V0. So I say again, we substitute this into here to replace V1, right? So that we get equation in terms of V0, and then by grouping V0 together and do algebraic manipulation, you get equation 4. Okay, therefore we have two equations now in terms of two unknowns, I0 and V0, right? This was derived from here by relating V1 and V0. Okay, then you solve these two equations with two unknowns. For two equations with two unknowns, the easiest way is substitution, right? Substitutions. Okay, here, let's substitute equation 4 into equation 1, right? Which means that you substitute I0 by V0. Okay, then you get the next equation. Okay. And after adding up V0, the corresponding coefficients, we get these equations, and using algebraic manipulation, we get V0. So the idea is that I substitute I0 in terms of V0, so that these equations, right? Equation 1 has only V0. If there's only one variable, then you can start using algebraic manipulation, right, to find V0. So this is my V0. So far everything is the same as the previous tutorial, is circuit analysis, right? Find V0, right? Find V0. The only difference for this tutorial is that we want to find the power. So we use V0 to find the power, right? Use V0 to find the power. Power is half V squared over R. Now this V0, right, is the modulus of your phasors. Okay, it's the modulus of the phasors. Okay, which means that you should express this in polar form with a modulus and an angle. Okay, but you just take the modulus. Yeah, just take the modulus, or if you do not want to calculate the angles, then go direct to calculate the magnitude. With this, basically this, right, is equal to 80, 20, and then you convert this into polar forms, right? It will be square root of 2, 1 square plus 1 square, right? And then this angle is basically 45 degrees. Okay, so we know that deviations, right? Magnitude, we only focus on the magnitude, is 80 divided by root 2. Then we get this magnitude, we square it, divide by R is 10, and then divide by 2. We will be able to get the average power. So squaring this, we get 6400, right? Divided by 2, 2 multiplied R, you get 20, and this half, right, come from the definitions of the average power by using peak values. So it's equal to 160 watts. So I hope everybody get the ideas. For power, it's just that you have to know what signals to find. right? What signals to find? So you find the signals first, based on circuit analysis. Then you use that signals to calculate the power. Okay, as I mentioned, you can also do it this way or this way, all right? Not only this, but for pure resistor, I take note this pure resistor because Ohm's law apply. I can substitute either current or voltage by the other variables. So for voltage, this is how it's calculated. For current, you use I square R half, okay? Or you want to calculate both voltage and current, right? Then you use half V I. Okay, I'll show you this one. Okay, if you want to calculate using current, also no problem. Your problem becomes finding current I1, right? Finding the current I1. So here we have already found V0, so I just continue from here. V0 is calculated just now, right? We got this one. So we use Ohm's law to calculate I1. V0 divided by 10. So this only scale my magnitude, right? Scale my magnitude. In fact, you can see that the phase angle do not change, right? Because we only divide by 10. Your magnitude reduces from 80 over root 2 just now, right, to just 8 over root 2. Okay, and over here, my magnitude is 8 over root 2, so I square it, multiply by 10, divide by 2, that means times 5, right? And then you can check that it's also 160 watts, same thing. So therefore, if you want to find average power using current, then your problem reduces to finding I1. Then calculate power using half I1 square R. Any questions? Okay, similarly, in AC circuits, you can also find the maximum power transfer, right? Maximum power transfer. Now, for maximum power transfer, no other way, right? Just use Thevenin's. Once you see a question is asking you to find maximum power transfer, it means that you must first convert these circuits into its Thevenin's equivalent form, right? Thevenin's equivalent form. Then use this to find the maximum power. Okay, in the sense that your maximum power is related to these two parameters. Okay, why you use Thevenin's is because that this Thevenin's circuits is easier to analyze, right? It's just a series combinations of two components, and you can easily use it to derive the maximum power, right? Now, the only difference now is that we have a load, okay, which consists of a real part and an imaginary part, right? A real part and imaginary part. L stands for load. So therefore, our Thevenin's equivalents, similarly, our Thevenin's equivalents, right, also are represented by phasors. Your source is a phasor. Your ZTH is also a phasor, right? In rectangular form, it's RTH plus J ZTH. Now this is shown in the load, right? You read through your notes. The matching conditions now becomes ZL, right? The load reactance must be equal to the negative of your XTH, right? XL load must be equal to negative of your XTH, Thevenin's equivalent. Okay, well, for the real part, it is the same. Okay, it's actually the same. Okay, these conditions can be easier represented in this form. ZL is equal to ZTH asterisk. Asterisk means complex conjugate. Complex conjugate means what? Reverse the sign of your imaginary part. right? Which means that if you have ZTH with a real part, imaginary part, then the complex conjugate means that this is equal to RTH, reverse the sign of your imaginary part. Right? Take note, is reverse the sign, meaning that positive become negative, but it's negative, then it will become positive. Right? So this is called the matching conditions for maximum power transfer. It means that in order for your load, right? In order for your load to get maximum power from your circuits, okay, this is the equivalent form. Okay, I must design the load so that it matched by ZTH. Right? In what way? ZL must be equal to the complex conjugate of your ZTH. Right? Then maximum power will be drawn. So you must remember these conditions. Okay, or basically is this condition. Right? Either way is fine. Well, I think this is easier, right? Because for the resistor case, remember you just have RL equal to RTH. So for impedance form, there's this additional cross. Okay, ZL equal to ZTH complex conjugate. Right, so this is easier to remember. Okay, next is to look at the maximum power. So this is the matching condition. It means that my load must be equal to the complex conjugate of my equivalent impedance, right, of the Thevenin's equivalent circuits. Okay, but what is the maximum power? Now take note that if your load, right, if your load is the complex conjugate of ZTH, right, which means these conditions. Okay, actually when you add them up, is a pure resistor. Right, these two are in series. These two are in series, and due to the fact that ZL is equal to negative ZTH, these two basically will cancel each other, right? Because they are reverse sign, equal magnitude, reverse sign. Okay, next, ZL is equal to RL is equal to RTH, right? So this is RTH. So therefore, when you add up, it becomes 2 RTH. This means that actually this whole load, right, this whole impedance actually is behaving like a pure resistor of 2 times of your RTH, right? 2 times of RTH. Okay, which means that if I want to calculate this current, because these are in series, it's just VTH divided by 2 RTH, all right? VTH divided by 2 RTH. Okay, which also means that your current here is actually in phase, okay, with your VTH, right? Okay, next, if I would like to calculate the power, right, the maximum power consumed by the load, okay, then since I know the current already, I'll just use I square RL, right? I square RL, right? In fact, you put this I square into here, and RL is equal to RTH. Then actually you can check that the maximum power transfer is VTH squared divided by 8 RTH squared, right? So where does this 8 come from, right? Remember, here you have half. So when you square it, then you have 1 over 4, right? And since you're using the peak values, you have to half it again, and then you get 1 over 8. So this is referring to the maximum power consumed by the loads, okay, from these circuits. Is VTH squared divided by 8 RTH. If you use maximum peak values, right? Take note that this is for peak values. Any questions? Okay, which means that to find the maximum power, you need to find VTH and RTH, right? VTH and RTH. Okay, and the next question actually is not to find the maximum power. So take note, is to find the value of your loads. Right, design this load so that maximum power can be drawn from the remaining circuits. Right. Okay, this means that you only need to find the load so that maximum power can be drawn. And what is that? Okay, remember just now I've shown the condition is that ZL is equal to ZTH compressed conjugate. Okay, which means that this load should be equal to ZTH compressed conjugate, right? So this is what we want to find. So your questions reduces to find ZTH of your circuits, right? Of this circuits. Find ZTH of your circuits. So you must look at the question first, because this may save you a lot of time. This question do not need you to find VTH, right? You never say find the maximum power. You say find the value of ZL for maximum power transfer, which means that I should only focus on my ZTH. So my problems reduces to finding the Thevenin's equivalent impedance of these circuits, right? Of these circuits. To do that, remember, right, there's a fixed step. First, you remove the load. Okay? Always first remove the load. This is the load of interest. Right? You remove the load, there's open circuits. If you want to find VTH, then you find the voltage across this open terminal. That will be your VTH. But here, no need to find. So don't waste time. Go straight to find your ZTH. Right? Go straight to find your ZTH. To find ZTH, you have to set the independent sources to 0. Correct? Set the independent sources to 0. This is how I remember voltage. Voltage equal to 0, short it. Current source, current equal to 0, open it. Right? So I short my voltage source and I open my current source. That means I kill the independent sources, or I set the independent sources to 0. Okay, then ZTH is the equivalent impedance across this terminal, right? Across this terminal. That means that you would like to find an equivalent impedance, ZEQ or ZTH, across with respect to this terminal. So this whole thing, right, must be simplified into one equivalent impedance. Now, if you are familiar with this series parallel combination, you can visualize easily. Just write down this equation, because these two are parallel, right? Because this is the same node. This is connected to here. So one end is connected, the other end is also connected, which means parallel. So same thing, right? This end is also connected together, and the other end is also connected together, so they are parallel. Right? If you cannot visualize it, right, just redraw the circuits, because this is just one wire, it's just one node. Right? So basically, these circuits can be redrawn this way, which means that both are connected to the same terminals, right, on either side. In that case, we say that it is parallel. Right? A parallel combinations can be easily simplified. All right. In fact, we know that if you have this parallel this, the notation is this: 40 parallel 40, 80 parallel negative J10 is this notations. And what this notation means is that Z1 Z2 divided by Z1 plus Z2, right? Z1 Z2 divided by Z1 plus Z2. Okay, but take note that if you have two resistors of the same value in parallel, okay, as I mentioned to you, the value is always half. Correct? The value is always half. Right? In fact, if you don't believe, you just put this: two resistors in parallel, R1, R2, both the same, divided by R1 plus R2. Then it's basically R squared over 2R, right? Which is basically half R. So if you understand that, then just write down 20. Right? If not, you press calculator, it will still give you 20. Okay, as for the other one, Z1, Z2, Z1 parallel Z2, right, is equal to Z1 times Z2 divided by Z1 plus Z2. Right? Z1, Z2 divided by Z1, right, plus Z2. Z2 is negative J10. Right? Okay, now you can see that you have three series components after you reduce from parallel, right, to one equivalent forms, and after that they are in series. I can add them up. So this means that I have J10, J20 in series, right, in series with 20, and in series with this impedance, right? So finally, what you need to do is to convert this into rectangular form because you are performing addition, and then sum up the real part and the imaginary part, you get one equivalent impedance. So far, what we have done is that we have found the equivalent impedance of this whole circuits, right? And then remember, what we want is not just ZTH, but rather we want to use ZTH to find the complex conjugate. Okay, here your imaginary part is positive. You reverse the sign, it becomes negative. Right? So take note of that. If this is negative, if your ZTH has a negative imaginary part, then you reverse the sign, it will become positive. Right? Just because this is positive, you reverse the sign, it becomes negative. So this is your load impedance. This is how your load impedance should be designed, so that maximum power will be drawn, right, from the remaining circuits. And since we need not find the maximum power, we can stop here. We do not need to find VTH for this problem. Any questions? Okay, in the previous two questions, we have used the maximum values to calculate the power, right? But actually in power engineering, right, we have another way of calculating the powers, okay, which is based on what we call the root mean square values. Okay? So for question 3 onwards, all your signals are represented as RMS value, which means that this is RMS value. Okay, let me first explain what is RMS value. Okay, previously we have seen the peak values, correct? If you have AC signals, this is actually the peak values, and AC signal is periodic. You repeat myself over one period, and the first half cycle is positive, the second half cycle is negative. Okay, this has a problem if you want to calculate the average values of this current, this AC current, because if you integrate it, right, with respect to one cycle, divide by one period, you get 0 because integration is the area under the curve. Here you have a positive area, you have a negative area, so when you add them up, it becomes 0. Right, this is very misleading because there's certainly an effective current, okay, which is not 0. There's certainly an average current, which is not 0. But if you calculate it this way, right, if it give you 0, right, so this way is not a good way to calculate your average values of your AC signals, because AC signals is symmetric over one period with a positive cycles and the negative cycles. Okay, and we know that if we square the signals, right, which means that if you square the signals, then everything will be positive, correct? Everything will be positive. So if we calculate the average of the square values over one period, then it will not be 0 anymore, right? So the idea is that we square it so that we have positive values. so that we can calculate the effective values over one period. Now, since we square it, right, to calculate the average value, we have to take square root. So this is called root mean square. Right? You square it, calculate the mean, then you take the square root back, and that is actually your RMS value. Now it can be shown that actually if you use these signals, integrate it, right, with respect to time, in the end, substituting t equal to 1 period, t equal to 0, you will just reduce to this, right? You just reduce to this. So check your notes. This, it can be shown that this can be simplified to Im divided by root 2. What is Im? Im is the peak values, right? Which means that if you want to calculate the average current within one cycle, what you need to do is just to take the peak values and divide by root 2. You take the peak values, divide by root 2, and that is the effective current within, or the average current within one cycle. Right, so to summarize for AC currents, the effective values, right, is the RMS value, which is the peak values, divided by root 2. So similarly, for any signals, given the peak values, you divide by root 2, will give you the RMS value. Now this tutorial is about AC power. Let's go back to our AC power again. Just now, based on the peak values, right, the average power was half V peak I peak cosine phase angle between them. Okay, now we have this new informations. It can be represented as RMS value. Okay, if you multiply these two together, multiply this by this, you can see that 1 over root 2 multiplied 1 over root 2 is half, right? Which means that this half VNIM can be replaced by VRMS IRMS, right? VRMS IRMS cosine pi. So this is easier to remember, okay? Because we know that power is V times I. The only thing is that now for this AC circuits, you have to multiply by the power factor cosine theta. Okay, for average power absorbed by resistors, you can see that by using the RMS value, then is similar to what we have learned, right, in week 1 and week 2, I square R, V square over R. So this is called the effective current. You square it, multiply R, you get the average power, right, or effective power absorbed by a resistor, right, or you can use VRMS square over R. So I suggest that even if you are given in peak values, use this to convert to RMS value, and then start, right, using RMS value, okay, directly, okay, which means that you can ignore this half, right, because RMS value has taken that into account. Now we know that, right, average power, if using the peak values, right, you use half VMIM cosine theta. If using RMS value, then you use VMS IRMS cosine theta. Okay, next, we know that phasors are complex numbers, correct? Phasors are complex numbers. You have a voltage represented by a modulus and an argument. So you have a current signals also represented by a modulus and the arguments, the magnitude and the angles. Okay, which means that V has a magnitude and an angle, right? This is called modulus, this is called argument in mathematical terms. And similarly, we have this magnitude and angle, modulus and arguments. So the next question is that, right, can we calculate the average power, okay, based on something we call complex power, since the signals are complex number, right? Rather than calculating your peak values first, take the phase difference between them, can we make use of the phasors to directly calculate the average power? Now, naturally, you think that, right, if you use the peak values, then you use half VI. If you use the RMS value, then you use VI, right, to get the complex power. Okay, but be careful that if you are multiplying two phases together, right, then you add the angles, right? You add the angles. So this means that if you multiply these two together, your angles will be theta V plus theta I. Okay, but we know that average power, for average power, we need to get the phase difference between them. Phase difference, not the additions of the angles. Okay, this basically is to say is that this won't work, right? This won't work. And in fact, I'm trying to explain why we add this asterisk here in your notes, right? Because if you don't do that, right, what you get is the sum of the angles. It's not the phase difference between them. Okay, and actually, the purpose of putting this asterisk there is actually to make your currents, right, has a negative values over here, so that when you multiply them together, that means we multiply V by I asterisk, then actually you get the phase difference between them. Right, so actually we are trying to define in a way that we can get the average power, right? Define the way that we can get the average power, which means that if we multiply this by its complex conjugate, okay, which is the negative of the phase angles, we will get this phase difference. Now you have to also understand that, right, by calculating the complex conjugates of I in polar form is just to reverse the phase angle. In rectangular forms, complex conjugate, right? Complex conjugate is x minus j y. Just reverse the sign of y. In polar form, you can just substitute the positive angles by the negative angle. Right? In fact, it's quite easy to answer this. Arctangent y over x is negative, right? Arctangent y over x. So it's actually the reverse of the angle. Okay, this means that if rectangular form, you just reverse the sign of your imaginary part. In polar form, you just reverse the sign of your phase angle, right? Your angle over here. Now, then, right, when you multiply V by I, you get a phase difference. So that later on, when you take the real part of this complex power, you actually get your average power. Same thing. Okay, at the same time, we have additional informations. We have the imaginary parts which give us the reactive power. Right? So complex power is a good way to calculate the powers, in the sense that you can just multiply them in phasor forms, and then take the real parts, you give you the real power. Take the imaginary part, you will give you the reactive power as well. Okay, well, the previous part is still the same. You need to find the voltage and the current, right? The only difference is that you need to take complex conjugate of a current, then multiply them together, decompose back, convert back into rectangular form. Right? The real parts will be the real powers. The imaginary part will be the reactive power. So as I said, the real part is the real power or the average power. Right? As for the imaginary parts, there are basically two types of loads, right? As I mentioned, inductors and capacitors, or combination, right? Combinations of them. So the reactive part, notice that for inductors, right? Remember this way, you have positive reactance. Capacitors, right? Negative reactance. So therefore, for capacitive load, right? Actually, your reactive power will be negative, okay? Because you have negative reactance, right? So you use I square, right? X, you get negative. I square X, you get positive. Therefore, for capacitive load, I say again, you get negative reactive value, which means that this will be negative. Okay, for inductive loads, you will get positive reactive power. Right? Positive reactive power. It means this will be positive. You must remember this part. How do I remember it? I just look at inductor positive, capacitor negative, right? So same thing for capacitive load, negative, right? Reactive power. For inductive loads, I'll have positive reactive power. And you also need to remember, right, whether is it leading power factors or lagging power factors. Okay, why? Because sometimes, right, the problem says that it's leading power factors. It's actually trying to tell you that your reactive part is negative. Right? Sometimes it gives you negative power factors. It's actually trying to tell you that your reactive power is positive. Okay, and there's a very easy way to remember all this. This has nothing to do with circuit analysis, right? But rather it is just a way of remembering, right? Which lead what, right? Remember we have this slide for inductive, I lag V. For capacitive, I lead V. Okay, as I said, this is not circuit analysis, it's just a way for you to remember it. Okay, this word will help you remember it, Sievert, right? Inductor L, capacitor C, right? My voltage is my reference. My voltage is my reference. For capacitive, I lead V, leading power factors. I lead V, right? For inductive, I lag V, right? I is lagging behind my V. I is lagging behind my V, which means that if you cannot remember it, just write down this. My V is my reference. Capacitor, I lead V. Inductor, I lag V. All right, or you go back to basic as I explained to you just now. This is how it works. For capacitors, right? I is lagging behind your V, right? Because you're dividing by 90 degree, right? So it's become negative. For capacitors, dividing by negative 90 degree, so I become leading, right? Or you want to remember in a fast way, just do what I did just now. Write down this word. You tell you which is leading, which is lagging, right? Okay, let's go back to the complex power. So by writing down this word, right, it helps. That means that if it's capacitive load, right, capacitive load, then you know capacitive I is leading V, right? Or you know leading power factor, it also tells you that it's capacitive load because leading, I lead V, so it's capacitive, right? And it's trying to tell you where the sign of your reactive power. Okay, this complex power, right, is best computed by this power triangle. Okay, in a triangle, you know that you only need two informations to find out the other information. Right? For example, if you know S and theta, you can find P and Q, correct? If you know P and Q, you also can find S and theta. So basically, you only need two of the informations to find the rest. So therefore, in the specifications of your power, of a complex powers, right, they are in various forms. Sometimes you're given S and theta only, right? Sometimes you are given, right, maybe P and Q. Sometimes you may be given theta and P only, but in any case, you can always find P and Q. Right, so we like to represent the complex power in terms of P and Q. Sometimes it may be given directly, sometimes it may be given indirectly, but given any two of the information, you can always find P and Q. Right, so the idea is that given two of the informations, you can always find P and Q. Okay, the other thing to take note is that you have to know the units of each of this. Okay, P is watts, right? This one is clear. We have done it so many times. The only thing new is that, how about Q? Q is actually, right, remember by this R term. R means reactive, right? Reactive. VA is units of voltage and current, volts, ampere, correct? Volts, amperes. So without the RL, it's just the apparent power, VA. Voltage, current, reactive is watts. Right? So remember the units because it actually tells you, right, which part of the triangle is given. Okay, let us move on. So we know that for inductive loads, right, inductive load, I is lagging V. I is lagging V. So usually when you plot the power triangles, right, because for lagging power factors, Q is greater than 0. So we put the triangles, the reactive part upwards, right? As for capacitive loads, I is leading V. I is leading V, leading power factors, and your reactive power is 0. So usually we draw the triangles, right? The other way around, indicating that this is negative, right? This is negative. Now, let's move on to question 3. Okay, in this circuit, you need to find two things, power factors of the source and the average power supplied by the source. And in these questions, all the signals are specified in RMS value, right? That means that this is RMS already. Okay. RMS is peak value divided by √2. So the peak value is 120 multiplied by √2 in other words. Okay, I will show you the overall formulation first. This is how I will deal with this problem. I'll simplify this whole thing into equivalent impedance, right? I call ZT. T stand for total, or you can call ZEQ. Okay, then I can find this current, right? Using Ohm's law, I is equal to V divided by Z. Okay, to find the complex power associated with the source, right? Take note is the source. Now, if a voltage is applied across a load, it resulting in a current flow, right? Passive sign convention, positive, negative. Our source is the other way around. Your source is current is flowing out of the positive terminal. So we put a negative sign here, passive sign conventions. Complex power is V times complex conjugate, right? Remember, V times complex conjugate. Negative sign because is flowing out of the positive terminal, right? Remember, I say that passive sign convention, very easy to remember. Water flow from higher level to lower level, right? And then for active elements, okay, if you want to pump water from lower floor to higher floor, then you need an active source, right? Which supply energy. So for power engineering, the convention is that consume energy, you put positive, supplying energy, you put negative, right? Negative, that means that by conventions, by natures, current flow from high to low. If the other way around, you put a negative sign. Okay, I will first, if you cannot simplify this directly, right? Actually, by now, I strongly urge you to try simplify it directly, but if you still cannot, then just do step by step. These two are in series, right? These two are in series, so actually I can combine them. 10 plus negative J phi equivalent impedance in series, right? 8 and positive J phi in series, add them up. Okay, after that, these two are in parallel. They are both connected to the same terminal. So I use this sign, means what? Z1, Z2 divided by Z1 plus Z2, right? Z1, Z2 divided by Z1 plus Z2. Okay, which means that I can simplify this whole thing, okay, by using this one. Series, parallel, and then after that it is in series with 2, so plus 2. Okay, the rest is to do it carefully. Z1, Z2 divided by Z1 plus Z2, multiply them, convert it into rectangular form so as to perform additions. Then eventually you can show that this whole thing is equivalent to one equivalent impedance of 8.154 plus J 0.7692. Right, real part and imaginary parts. You can convert it into polar forms. Square of this plus square of this, square root give you 8.19. Arctangents of imaginary part over real part give you 5.389 degree. So we have a load, right? We have a load with this equivalent values. Now, take note that your impedance, the phase angles, can be used to calculate your power factor. Right? In fact, your power factor is cosine of this angle. Okay, why this is so is because this is just Ohm's law, right? Which means that if you have a voltage here, okay, which resulting in the current flow, I, right? So V is equal to I Z, Ohm's law, correct? So if your voltage is represented in phasor form, theta V. Here your current is represented in phasor forms, theta I, and your impedance, right, is also represented in phasor form, okay, R n theta. So I'll just put here R n theta. All right. When you multiply them together, what you have is that theta V will be equal to theta I plus theta. Right? So this causes the phase difference between your current and voltage. Right? In other words, theta V minus theta I, the phase difference is theta. Right? This means that once you calculate the impedance, actually you take the cosine of it, that will be your power factor. Right? And then the value of cosine, right, whether negative or positive, is always positive. So it's 0.9956. Now, how do we know it's lagging? How do we know it's lagging? Now, here I put lagging. You check your impedance, positive, right? Positive reactance, so it's inductive. Okay, inductive is lagging power factors, so we know that it's lagging. Okay? Or you can get it from here. Your voltage is this current plus this, correct? Current plus this. So your current is lagging behind your voltage by this angle. So we have obtained our equivalent impedance and we have used it to calculate the power factors. And we know that it is 0.9956 lagging. Okay, next is to calculate the current. Current is Ohm's law, V over ZT. V is given, right? Divided by the current, divided by the impedance. Right? In polar form, you can just divide this. It give you this value, and you subtract this. Right? You give you this value. So in the end, we get this current. But remember, we are calculating the complex power associated with the source, right? With the source, as I said, because this is the other way around of the passive load. So we put a negative. Voltage is given. I, we have found it over here, right? So what you need to do is to take the complex conjugate of the current. Right? Reverse the sign of this. Positive will become negative. Right? Before you multiply them together. Right? Be careful, otherwise you are adding rather than subtracting the phase difference between your voltage and current. Right? This is the phase angle of your current. This is the phase angle of your voltage. Your average power must be the difference between them. So take the complex conjugate so that you can generate the difference. Right? In fact, here you can see that it's also equal to this value over here of your impedance. Right? Okay, after that, this polar form, you can also represent it in rectangular form. And notice that there's a negative value of your real power. Right? This is the passive sign conventions. If it's a source, we put negative, meaning that it's supplying power. And you'll be absorbed by the load. Right? You'll be absorbed by the load. And we have calculated the average power based on the complex power. Okay, if you go back to this question again, right, it actually says that just calculate the average power. You never say that you use complex power, but I use these methods, right, just to show you the concept of complex power and how it can be used to calculate the average power. Okay, but if you want, you can also do it in the usual way. Right, that means that you find the voltage in phasors, find the current in phasors, find the phase difference between them, and since we use RMS value for question 3, we don't need to divide by half, but divide the 2, right? So we just use the RMS value of the voltage, the RMS value of your current, just now we have computed, and then take the phase difference between them, take the cosine, also same answer, right? Same answer. Okay, just to show you the other way, right, to understand the real meaning of average power, you can also use I square R, right? I square R. I is the current flowing through your load, right? I must be the current flowing through your load. R is the resistive part of your load, right? Only the resistive part consume real power. So I square R, you check it, it's still the same, right? So all this has the same value. It just means that in order to calculate the real power consumed by the load, the resistive part, okay, there are several ways. One way is to calculate V and I, take the phase difference between them, then use VI cosine theta. The other way is to calculate the complex power, and then take the real part of the complex power, right? It also give you the average power. But the complex power, one thing good is that it also give you additional information. Right? We know what is the reactive part as well. Right? And the complex power will be very useful, right, in the power factor correction, which is for next week tutorial. Any questions? Right, so for the next questions, it specifically asks you use complex power. So you have to use this, right? If the method is specified, do not deviate. Previous questions, up to you. You can either use this way, or complex power. For the next question, we need to calculate the complex power associated with the dependent source. There's only one here, right? Which means this, you want to calculate the power of the dependent source. Now, firstly, let's focus on this dependent source only. Okay, if I want to calculate the voltage, the complex power associated with the dependent source, you know that you need to calculate two things, all right? One is the voltage across it, one is the current flowing through it. Okay, at this stage, we do not know whether is it active or passive. So we use passive sign conventions. Complex power is voltage times complex conjugate of your current. We assume flowing from positive to negative, right? Let's assume flowing positive to negative. So therefore, you need to calculate two things, the voltage across this dependent source and the current flowing through this dependent source. Now this is a current source, right? Which means that this current flow in this direction is 2V0. Now we define this way from positive to negative, so it's negative 2V0, right? Negative 2V0. Okay, which means that I asterisk is actually the complex conjugate of negative 2V0, okay, which means that actually is negative V multiplied by negative 2V0 asterisk. Now, this means that to find the complex power, we need to find two things. We need to find V0 and V. We need to find this V0. V0 is defined in the circuit by the voltage across the 1 ohm resistor, right? This is defined. Now, V is what we define. V is what we define in order to find the complex power. Now, in circuit analysis, basically, it's something you do not know, just call a variable, right? And then you see how many unknown variable you need to find, and then you decide, right, on the number of equations to solve, so I have to get the unknown variable. So here we need to find two things. We need to find V and V0, right? We need to find V and V0. So since it's dealing with voltage, I'll use nodal analysis to find it. Okay, and I'll use nodal analysis to find V0 and V1. Basically, V0 is this node voltage over here. V1 is the node voltage I define for this unknown, right? These unknown nodes. And V0 is what we want, and V is also what we want, right? So I will just use V0 and V1, okay, to solve the problem, because why I do not define V as my node voltage is because V is related to V1 and V0, right? V is related to V1 and V0. Okay, if I look at this part of the circuits, right, just focus on this part of the circuits, and you can see that this current, right, flowing through the resistor comes from here, okay, which is 2V0, right, which is 2V0. So if you use Ohm's law simply here, then voltage across this resistor, V minus V1, right, because I assume current will flow this way, high to low, V minus V1 is equal to current flowing through it, Ohm's law, to IR, right, IR, current resistor. Okay, then if you bring this to the other side of the equation, basically you can get V in terms of V1 and V0, right? So I do no need to create, right, one more unknown, because it can be calculated if I can find V and V0. So this is my overview. I need to find the complex power associated with the dependent source, okay, which means that I need to find V and V0. I use nodal analysis to find V0 and V1 first. Then I use V0 and V1 to calculate V, right? So that after that, I can use it to calculate my complex power. So this is just the overview. As I said, before you try to solve the problem, right, try to have this overall picture first. In fact, if you can write this now, it's already half done. So I start with the first step. I'll find V0 and V1 by using nodal analysis. Nodal analysis is a defined node voltages already defined. Then each of the unknown nodes will give you one equation, right? So you start with node 1, inflow equal to outflows, right? Inflow, this node voltage is 24, 0. 24, 0 minus V0 divided by 4 is the current flowing through the 4 ohm resistors. Okay, the other one I will assume outflow because normally, right, this flow to ground, V0 minus 0 divided by 1, right, this current. Here I'll just assume outflow. You can also assume inflow, no different, right? You give you the same equation, V0 minus V1 divided by negative J. And simplifying these equations, I get one equation but two unknowns. Therefore, I cannot stop here. In fact, I only look at part of the circuits only. I have not looked at the other part, right? So I continue at node 1. I suggest that since you already put these directions, current directions, so leave it, right? So that you can directly copy it down. Now this one will become inflow to node V1. And this one I'll assume outflow, right? So outflow V1 divided by J2. This is my outflow. And then I have one more. This one is inflow. 2V0 will flow into the node. So I have plus 2V0. Inflow, left hand side, outflow, right hand side, right? Inflow equal to outflow. Then I simplify these equations. I get another equation. So I'm in a position to solve for V0 and V1 now, right? Because I have two unknowns and I have two equations to solve. Now, two equations with two unknowns is easy to solve by substitution. You just substitute one values in terms of the other one into the other equation so that there's only one unknown. All right, that means that if V1 is substituted by V0, then there's only V0. If there's only one unknown, the rest is just algebraic manipulations to get the solution. The only difference is that you're dealing with complex number, right? So you have to be able to convert it from one form to another. You have to be able to perform mathematical operations, right, on it. And finally, we can find V0 in phasor form, right? AC analysis phasor form, 2.05160, right? Take note that the angle is 160. Make sure you can get this one. As I say, if anything not sure, just put it into the 4 quadrants, and you know that, right? Because it is in this quadrant, therefore, it must be more than 90 degrees. Okay, after you get V0, put V0 into equation 2, you can get V1, right? You can get V1 because we want to find V0 and V1. So we have found V0 and V1 by using nodal analysis. Okay, next is to recall our overview. Okay, actually we want to find the complex power. To find the complex power, you need to find V and V0, right? So we use nodal analysis to find V and V0, to find V0 and V1, and then we use V0 and V1 to find V. And after that, we get everything to calculate our complex power. And so the next step is to find V. V is the voltage across your dependent source, right? Remember, V is the voltage, okay, across the dependent source. Okay, which is equal to V1 plus 4V0. Just now I've shown it to you. So after you get V0 and V1, right, just substitute into here, convert to rectangular form, add them up, and convert back into polar form. You can show that V is equal to 14.79, right? Angle 126.31. So we have obtained all the information needed. We have V, we have V0, right? We have V, and we also have V0 previously calculated using nodal analysis, which means that now you can proceed to calculate the complex power associated with the dependent source, right? Which is negative IV times negative V times I asterisk, right? I asterisk. So remember to reverse the sign of your V0, okay, because you're taking the complex conjugates, and then we will have a complex power with a real part and the imaginary part. Now here, actually at the beginning, we don't really know whether is it active or passive, right? This dependent source, we are not sure, because it will depending on whether the current flow in or out of the source. Okay, we assume in, but in the end, right, you get a negative value. So this actually means that this dependent source is supplying power. So because it's negative, right? Negative power means supplying. So it's supplying a power, average power of 50.45 watts. Any questions? Okay, for the last questions, right? Basically, you need to find this current of a combinations of loads. Right? Notice that the loads are specified in various ways, different way. All right. Actually, remember I told you power triangles. You only need two informations to find the complex power. Complex power consists of real part and imaginary part. Right. So actually, all this are given in various form. What you need to do is to convert it into this complex power. Right. In fact, it means that you're given two informations of your power triangle. You need to find P and Q, right? This is what it means. Okay, I will call this one S1, complex power 1. I'll call this S2, it's just a numbering, this S3, right? And I need to find the real and imaginary part of my complex power for S1, S2, S3. Okay, and then I add them up, right? I add them up. This will give me the total power, right? Total power of this load. I take note that you can just add up the power regardless of series parallel. No need to worry about the series parallel. Series parallel will only, right, be used if you need to calculate the current. In this case, we don't need actually, right? So we will just add up the complex power. And after you add up the complex power, you can use it to calculate your current, right? Because this complex power, voltage across it is V0, right, given. Current flowing through it is what we want to find. Right, so we know this one, and we are also given this complex power S1, S2, S3 over here. So the only unknown is this one. This means that you can solve it directly. I0 asterisk is S1, S2, S3 total divided by V0. Right? These are complex numbers. So let us start with S2. I start with S2 because it's easier, or it's the easiest among these three. Right? In fact, look at the specification, 1.2 kilowatts. Just now I specifically reminded you, right? Look at the units. This means what? The real power is given. Secondly, 0.8 K VAR stands for reactive, right? Reactive. So this actually is to tell you that you're given P and Q already, right? You're given P and Q already, and P and Q has two possibilities. It can be positive or negative, correct? It can be positive or negative. So how do you know positive or negative? Here, this is a clue, capacitive. Right, capacitive, then you have to know that for capacitive loads is leading power factors and you have negative reactive power. right? So by saying that it's capacitive, it's telling you that you have a negative reactive power, right? Okay, as I told you, right, capacitive is negative J over omega C, right? So remember this negative capacitive values, okay, which means that it's actually 1200 watts kilo, right? The reactive part is actually 800, and because it's capacitive, we know that it's a negative, right, reactive power. Or if you want to put in kilo form, right, that will be 1.2 kilo, 0.8 kilo, right? It means 800,002. Okay, so we have obtained the complex power of this load. Let's move on to S3. Now, S3, right, look at the problems. You're given the real part of the complex power. You're also given the angle, right, is 0.9 power factor lagging. Now, let's look at the power factor triangles. It means this angle is given and this power is given. And you need to calculate the Q, right? You need to calculate the Q. Why do I say the angle is given? Because power factor is cosine theta, right? Power factor is cosine theta. It means that if you're given the power factor, you're given the theta. Okay, but you need to determine the sign of your reactance, right? Reactive power. So go back here, lagging, correct? Lagging. So what is lagging? Lagging means inductive load. Right? Lagging behind is inductive load. Inductive load is positive reactive power. Right? So this is positive, which means that okay, if you go to the power triangles, okay, I'll first find the angle of the power triangles using the power factor. Arc cosine 0.9 is 25.85, right? Press calculator. Then I look at the power triangles. I'm given this information from the power factors. I'm given this real part, right? So to find Q is actually 4 kilowatts, which is this one, times the tangent of this angle, right? In fact, tangents of the angle is equal to Q over P, right? Q over P is tangent of this angle, so therefore Q is P multiplied by tangent theta. Right, so remember, you're just given two informations to find P and Q, right? Some of the information may be given directly, some of the information may be given indirectly, meaning that you give a theta, give you this one, you can still find Q, which is 1,937, right? Means 1.937 kilo. I take note, positive. Why? Because it's lagging, right? Lagging means inductive. Therefore, it's positive reactive power. Okay, lastly, S1. S1, notice that you're given 2 kVA, no error. So this is the apparent power, right? And then 0.707 power factor leading. This basically means that I'm given this angle between my voltage and current, arc cosine 707 leading, I lead V by 45 degrees. Now, leading power factors, I lead V means what? Negative reactive power, right? I lead V means lagging, right? Leading means positive, negative reactive power. I is leading V, so it's capacitive. Capacitive give you negative, right? Negative reactive power. So we know that we should put a negative sign here. And in this case, you are given this part of your triangle. Right? This VA, no error, means apparent power. And you're given the angles. Okay, to find P and Q is just to project, right, onto the horizontal and verticals. 2 cosine 45, 2 sine 45, they are equal. 45 means same length, but take note this is less than 0, right, because it's leading. So therefore we put a negative sign here. Okay, to summarize, right, given two informations of the power triangles, we managed to figure out the P and Q respectively for each load. This is called the complex power. Now, the total complex power is the summations of them, right? Regardless series parallel, just add them up. And it will give you a total complex power. Okay, based on that, I then can divide by my voltage across it to calculate the complex conjugate of my current. I take note that this is the complex conjugate of the current. So to find the actual current, right, you have to reverse the sign of your imaginary part. So let's proceed to add up the complex power and then divide by the V0, right, which is given. Okay, if you add them up, adding up the real part in imaginary parts, you can check that is equal to 6.61 kilo, right? Be careful. It means 6,610. Minus J 0.277 kilo means 277, right? And this means that the load is actually absorbing power, right? Positive, absorbing power from the source. Okay? Okay, next we divide by V0 is given in these questions, and then in divisions, right, you may want to convert to polar forms, numerators, and then do the divisions. You can check that it's equal to 3.1 magnitude, angle negative 92.4 degree. Right? So remember, this is the complex conjugate, right? This is a complex conjugate. To get back the current, you have to reverse the sign. Okay, so to summarize, you convert all the complex powers in various specifications into the real and imaginary part, add them up, divide by voltage, you get the complex conjugate of the current, then you reverse the sign of the imaginary part or the angles to get back your current, right? So this is how you can calculate the current from the complex power. So take note that, right, this complex power associated with a load. If you want to calculate the complex power associated with the source, right, actually by conservation of energy, you just reverse the sign because this energy must be supplied from somewhere, right? So the supply must be equal to the one consumed, right? It means that you add them out, it must be equal to 0. Okay? Therefore, is this positive, this will become negative. If this negative, this will become positive. You just reverse the sign. So this, the conservations of energy. So this end of the tutorial, just a brief remark over here, guys. In fact, some of you may be wondering why I can just add up this power without considering whether a series of parallels. So here I just show it to you. Right? If if let's say you split it into two parts, all right, so this one is S1, this one is S1 plus S2, or if you want to further split it, you also can, but here I just show you S1 plus S2. So here the current flowing through S1 and S2 are different. Let's call it I1, I2, right? But for the complex power associated with S1 is the voltage across it, V0, multiplied by the complex conjugate of I1, right? So this is true. Okay, next, the voltage across here is V0, multiplied by complex conjugate of I2 is equal to S2 plus S3. Now, if you take Kirchhoff current law at this node, inflow is equal to outflow, I1, I2, correct? So this means that this I0 total current is I1 plus I2. Now, if I add these two equations together, okay, on the right-hand side, I'll have S1 plus S2 S3, straightforward, right? Right-hand side. The left-hand side, take note that you have V0, and then you have I1 asterisk plus I2 asterisk, okay, which is actually equal to V0 I0 asterisk. Why? Because I0 is I1 plus I2, so it's still the same, right? Eventually, even if you split them, right, make no difference, it's still the same. So another way to solve the problem is this way. You find S1 in complex power form, divide by V0, right? You get I1. Remember to reverse the sign to get back I1, right? Then you find S2, S3, divide by V0, you get I2, complex conjugate, reverse the sign, you get I2, add them up, you also can get I0. Right? So you can do it this way, or if the question asks you find I1, I2, then this is the way that you should do. Any questions? Any questions? Okay, if not, that's all for the tutorial today. Thank you.